It's up to you.
So I started the attendance thing, I keep forgetting, so I started the meeting itself, so say yes if you're present physically. So that's, anybody has been to Berlin? No? So that's Brandenburg Gate, and I like this because if you keep track of the current European politics, Germany is pretty much the only thing that wants the European Union to survive. It looks like they're desperately trying this. But anyway, this is midterm information. I assume that you all currently had post-traumatic stress or something. I don't know. Nobody's here right now. So anyway, so it looks like most of you thought that midterm is actually a failed exam, which is good. Some of you, 35% of you thought you did quite well. I don't know who is who, by the way. And then, of course, about 60% thought they struggled. Anyway, that's where it is. I guess normally any reasonable exam is probably a fair distribution, depending on, I don't know exactly what the students have put in class. So we did do, I mean, the actual exams will be returned hopefully next class. We did like one pass, and there's going to be some fine-tuning to be done. But currently it looks like, I mean, it's not final, average is about 67%, standard deviation is about 15%, and high is 95, low is 30. That's where it is. So you can start worrying where you are in that particular. So one thing that we are thinking of, and as a possible option, is so since a large number of people thought they struggled, even though the exam was failed, there is a possible option that we are considering. It's not guaranteed, but we could put the midterm as an optional homework on the blackboard. Okay, so this would be auto-graded. So you get a second chance to do the midterm, but it will not count anywhere near the level that the in-class exam counted. So it will be a small percentage, and it will be seen as an extra credit homework. So before we take the time, actually we have to do that. We have to convert that into a blackboard repeatable fashion. So before we do that, I wanted to see whether there is any interest in having that option. Remember, you don't have to do it. Even if I put it up, you don't actually have to do it. You know, it's an extra credit. And in this class, just so you understand, extra credit is really used as extra credit in the sense that the extra credit marks that you get anywhere, including on the projects, they are kept separately. And when I convert numbers into letter grades, I don't look at them first. So basically, we make a threshold, a cutoff based on normal, cumulatives. And then if your extra credit pushes you over a particular line, then you get a better grade. That's how it happens. So you don't need to worry that because I'm providing an extra credit option, it's not really an option if everybody else just stops living and starts doing that. Okay, so but I want to actually get a sense of whether there is any interest in that, or people are thinking enough is enough, let's move on to something else. So how many of you would like an option to be able to do the midterm again as an optional homework? Remember that it's not going to replace your midterm grade, it might be almost like another homework. Okay, how many of you would like that? It'll be an extra credit. It's optional. Even if you actually raise your hands, you don't have to do it. And if you don't do it, it won't just get on. Okay, looks like a lot of people are interested. So that's something that we will try to. Marius has agreed to spend time converting the Word document into a Blackboard readable format. So, which also means that we won't give until that happens, and then a timetable for that is set. We won't actually give out the solutions for the midterm. Okay. I assume that you may already have talked to people because you didn't know I was going to do this about midterm, but it would be nice if you don't actually work together to do that midterm interested, you could try to do that. Okay, also, again, remember that this will be in parallel to everything else that's going on. Okay, nothing is going to stop. So there is going to be reinforcement learning project that's due tomorrow, right? Because I'm always supposed to be on Halloween day. And then we will give you a neural network homework and a neural network project. Because right after the reinforcement learning will be the neural network project. After all, we took this course so that you can put on your CV that one day you started TensorFlow. And so you should do that. And then, so that's basically, so just think of this, don't yell at me because I gave you an option. We always provide the rope. What you do with the rope is up to you. Okay, so that's that. Any other questions on the exam, midterm, what's going on in the course, etc., etc.? Yes.
Is there going to be 4 projects or 5?
I'm hoping for 5. Okay, but certainly 4 because the 4th one is going to be given. And I think it would be due sort of around November 20th, and then they normally I try to do a smaller project for base networks. That would be the last one. So that doesn't require too much work. But that's basically what's happening. Any other questions? Yes?
Any idea about the final exam?
So when is it due?
Yeah.
They didn't tell us. I told you it would be in that week. That's all I know. I did send a mail. They are supposed to make the schedule available. They haven't yet. Okay? So it's sometime that period. Yes?
Does question 2 on homework 3 still be changing, or is that already been resolved?
I don't know.
It's not resolved yet. Not resolved? It's not.
Yeah. Okay. But as long as questions get answered, participation, I'm very happy. Okay. Any other questions? They changed the tone. Any other questions? Yes?
Your grading scale, are we going to talk about it at all, or
Like what?
at the end of the semester?
So I'll just say the following thing. I normally send these things. I'm sure I said this in the beginning. I am way more interested in making your life miserable during the semester than after it, if you get my okay. So it doesn't really matter. I'm not interested in making everything easy and then split hairs between 99 being an A and 98 being a B. Okay. So it depends on how the class does, but in general, my philosophy is that you should basically work very hard during the semester, and you would not. Most people are surprised at the grades they get in a positive way. Okay. That's the only thing I say. Yes.
One more question about that. Do you distinguish between graduate and undergraduate? Do you split the class
We
averages?
actually, so that's a very interesting question. I don't know because honestly, the graduate students are essentially taking it as a 4-level course. At one time, it used to be that there will be 471 and 598. And so they will get the 598 level credit. So graduate students are taking it as a 4-level course. Okay. So in theory, I am actually not supposed to distinguish because they're all doing this. So for example, there could be an undergraduate student who's taking just this course and nothing else. And they would do better probably because they have more time. And presumably grad students are in a similar situation. I realize that undergrads are taking 6 courses and also doing other stuff, and grad students take 3 courses, plus they're grad students. I realize that. But essentially they are paying the tuition, they are taking it as a 4-level course. Yes?
Is the first project going to be graded?
What?
Is the first project going to be graded?
What do you mean first project?
The project 1, part 1?
It's been graded, all projects have been graded.
Project 1?
You have to ask the TAs, because mine disappeared off my blackboard too.
Yeah, mine disappeared too.
Yeah, so basically there are crazy stuff about Blackboard, but the TAs have actually been very, very, very responsive. So they have graded things and put up, pretty soon after the project deadline, given that of course we have to wait like 5 days after each deadline because people might take extra 5 days, extra 3 5 days. But having said that, everything has been graded. If you don't see your grade, it could be because of some technical glitches that other people have actually said. Again, whenever you have these kinds of things, put in a private question on the piazza. Other people are doing it. Yes, sir.
Would it be possible to get like maybe like an email sent with a list of everything that's been graded so that we know to ask about certain things? Because I know not everything's been graded.
Everything's been graded.
Everything is?
Yeah.
Yes.
Okay.
Yeah, the TAs have no life.
Cool.
It has been. So you can assume that it's been graded. I mean, in fact, in my life, I don't think we ever had midterm graded like right after the class when the midterm was held. If I am basically doing it myself, it would have taken multiple weeks. So they actually, are very, very nice. They're helping a lot. Any other questions? Okay, so one last question. So how many of you have the bias remorse about having just one midterm as against 2 midterms? I'm curious. How many people wish there were 2 midterms? But still there are enough sturdy people who are happy. So you know who those 35% of the people are who did well. So if the guy next to you did not raise their hand, when you go out of the class, you know what to do to them. And then the curve would be much flatter. Okay. Fine, let's go forward. There's no other questions. Again, remember I said there's a attendance thing out that software TV is taking. So if you're present, say yes. That's basically the thing. So what I'm going to do today, and as I said today, also we will be taking this extra 25 minutes. That will complete the time you owe me for the next class. You gracefully decided to be at any rate. So, and then what we're going to do is complete the discussion about neural networks. As I said, there's just so many things, and probably a lot of them are particularly timely for you, but we will do as much as we can in this class, and then we'll move on to other things. We might very well come back to some pieces of it again, things like autoencoders and generative adversarial networks. I might mention them in the context of Bayesian learning when we get to Bayesian networks. Unfortunately, there's only 1 month left. I don't know where the time went, but that's the reality. Okay, so basically, you remember that we talked about, of course, we did some exercises with just to get you back into the mood for neural networks. We did some exercises on the TensorFlow playground to get a sense for classification learning. We understood the difference between classification and regression. They are both supervised learning algorithms in the sense that you've been given examples with labels. In the case of classification, the label is a class label, so it's a discrete label. In the case of regression, it is just a function value, so it can be a continuous value. That's the only difference. And then we talked about the fact that perceptrons are great in essentially learning linear separation planes, hyperplanes, in a classification scenario. Whereas in many cases when there are non-linearly separable, that means the separating plane is not a plane, it is a surface, then you essentially have to deal with multilayer neural networks. We looked at multilayer feed-forward neural networks as well as multilayer recursive networks, recurrent networks, where the weights actually are forward as well as backward. That means that the activations flow backwards as well as forwards. And mentioned that in fact brain probably has more these forward-backward networks rather than just forward networks. But in fact, forward networks are the ones that we basically focus on a lot. And then we looked at multi-layer feed-forward networks, and then talked about the fact that from an intuitive point of view, again, you're going to do gradient descent, and you know that in the context of perceptron learning, gradient descent involves updating weights a little by little. Basically, the amount of change is proportional to the gradient, and it was also proportional to the error. Okay, that's what we have seen. And one interesting question, of course, from an intuitive point of view, is you know what the error is at the last level because you know what the true output is supposed to be and what the network said. But if you think in terms of error, then you don't know what the error is in the middle layers because you don't know what they're supposed to be. Okay. However, we pointed out that there are like two different ways of thinking about it. Intuitively, you can think of the error at the middle layers as essentially sort of the lower layer error is proportionally shifted to the middle layer units. If you have the last layer which has a particular amount of error and there are 3 units above it, then these 3 units are being connected to this last layer unit with weights W1, W2, W3. Then the error for each of them, the part of the error that this guy is making, that these guys are essentially responsible for, is proportional to the weight with which they are connected to that. So that is actually the intuitive way of understanding it, but it turns out that that's actually what chain rule tells you. Okay, so one of the interesting things is depending on where you read about back propagation methods and error propagation, in some psychology textbooks, for example, they'll say they came up with this approximation. It looked like a reasonable thing to kind of put the error in proportion to the weights. But actually, if you remember, I asked you, I don't know how many of you did this. Yeah, this one. I don't know how many of you actually did this, try to follow the steps because it's direct use of chain rule from your calculus. And if you do this, you essentially realize that that's what the chain rule tells you will happen at the middle layers. So there is actually nothing different. You're doing the same. What the calculus is telling you to do is what you're doing. Okay, so that's what while keeping in mind. And then, of course, we talked about, in fact, I know this way, we talked about role of GPUs in doing supporting back propagation on multivariate networks. We talked about the number of times back propagation was invented, separately rediscovered many different times, and some of the sociology of science that led to it. Then we also talked about the fact that gradient descent is really hill climbing in continuous spaces, and you can do hill climbing also for discrete spaces, for example, if you're interested. And that gradient descent for continuous spaces, the simplest idea of making the change in the weight be just proportional to the gradient. That's the first simple idea. But there are better ideas. In fact, one additional idea that we talked about is the momentum idea, where you look at the rate of change, and then essentially, if you are making changes quickly, then you continue to make changes. So if your last change is no longer just dependent on the gradient, it's also dependent on the momentum. It's the amount of change that's been happening. Okay? And so that sort of a thing will allow you, in a sort of a pictorial way, that will allow you to sort of escape small local minimas. For example, in this particular kind of a case, there is a little local minima here. If you're making very careful steps, you'll come here and you'll no longer move. Okay, whereas if you're just running down the hill, essentially, basically that's what the momentum the updates are going to do, then you're likely to essentially make a big step from here, which will put you on this side. Which means you just ignore, you just jump over the minimum. So this is something that's worthwhile understanding. Of course, when we are running, we don't actually jump over the minima. We do go through the minima and continue. But in gradient descent, essentially, what you're doing is you're changing the x-axis or the weight axis. And the weights will be changed so much that you're sort of going to get out of this and go to the other side. Okay, so that's the kind of thing that momentum will work, and then momentum kind of progress will work. But there are actually many other smarter ideas, which I'm not going to go into. But that's like a whole area of continuous optimization for multivariable functions. And in particular, I did point out that many of those ideas come from essentially this holy grail of trying to do Newton-Raphson method. Because one of the interesting things in Newton-Raphson method is actually, if you remember the discussion, is you're going to change x by x minus some quantity times the gradient. Notice that this quantity you can think of it as the learning rate alpha. Okay, except previously it was a fudge factor. You had to come up with a separate alpha and hope for the best. Here you're saying there is no fudge factor in the Newton-Raphson method. It essentially says the right value to put here is essentially based on the Hessian. Okay, except Hessians involve keeping track of the double derivatives, and that basically becomes too costly in terms of per step cost. So per iteration cost of gradient descent will be too high if you do second order methods, but they're actually more robust. And we talked about the fact that there are approaches which basically do second order methods like gradient descent, in particular LB, FG, S, which actually gets used in certain variations of neural network learning. In particular, I talked to you so first of all, this is the whole thing about Newton-Raphson method being the holy grail, and think of everything that's being done as trying to get closer to Newton-Raphson method without taking the hit of actually keeping track of the second derivative. That helps you understand why are there a whole book full of methods for gradient descent, instead of just one approach. Okay? And so in terms of using the second order methods, I mentioned that the pseudo second order methods were used, when I mentioned this particular slide, I mentioned that it was used for Deep Dream. I didn't have a slide at that time, and after the class I added the slide and essentially summarized what I said in the class. So this was added after the class. And in particular, what happens in deep dream kinds of scenarios, and some of this becomes clearer when we actually do combinates today at some level. In kind of deep dream kind of scenarios, you have already trained the network, however big it is. And now you are essentially training the image such that this network will start seeing you as a particular class. Okay, so in particular, essentially, you want to see in this picture a cat. So you keep modifying the pixels in this, little by little, until the network says with a higher confidence, yes, this is a cat. And apparently, by the time you did this, it became this way. And so it looks like all of us are on some kind of drugs. It does sort of look like this person, but it also looks like a cat. And so that sort of deep dream stuff happens. Okay. Okay. So we also mentioned why it is actually easier to dream cats and dogs and birds for basically the existing neural networks. It was because many of them were trained on this ImageNet database. ImageNet database is essentially, it was picked from the internet, and the internet is full of cats and dogs and birds. Okay, and so essentially it turns out that of the 1,000 classes on the ImageNet, more than 200 are dogs, and a whole bunch of others are like birds. And in fact, I think normal human beings can't tell that many dog breeds apart from each other. Okay, so you have to keep that in mind when later on today's class we will take great pleasure in how ImageNet accuracy has kept increasing, and now it is superhuman. It's better than humans. That's probably because humans have a life to live instead of keeping track of 200 different kinds of dogs. Unless you are some kind of a dog breeder, why the heck would you need to know 200 different kinds of dogs? You see what I'm saying? So again, it's a question of what are you comparing with what. This particular network was trained on data that was made up of large number of dog breeds and large number of bird breeds, etc. Now, when you're thinking about it, you should also be thinking about the fact that the way you train a learning system introduces biases. Right? It's when, how many of you have heard of this word if you just keep reading random New York Times articles or something? Algorithmic bias. Only one. So apparently nobody reads newspapers. So there's a huge worry now that somehow there is this algorithmic biases, and that cold, unfeeling algorithms are making biased decisions that are putting all brown people in jail, for example. Right? So the question then is, of course, it's not the algorithms. Nobody is going to sit down and write Okay, if the facial color is this much below this level of intensity, put them in jail just to be careful. Okay, they won't write that. At least we used to do long back, but now we have reformed by hypocrisy. We can't say it aloud. If we say it in actual code, somebody will read it and they'll all laugh at us. And I was actually in Germany, and Germans, one beautiful word in German is Schadenfreude. Do people know what Schadenfreude is? Schadenfreude is essentially, it's like that bozo got caught making this mistake, and let's all have some secret pleasure when they're being excoriated. Okay? So there was this issue of, well, only Germans feel Schadenfreude, all of us do. Of course we do, we just don't have a name for it in English, so we just copied it. But in general, coming back to this data bias situation, nobody writes biased algorithms, lest they will get caught later on. And then they will be on Twitter, they will be on various social media, and their jobs will be lost and all sorts of things. Instead, bias comes in a much more indirect way. It comes from the data that you use to train the network. So this was just dogs and cats, okay situation. Imagine you're training, I may have mentioned this at some point of time, imagine you're training to essentially tell the difference between professors and non-professors. Okay? So you go to Google image search and say professor. And take all those pictures and say those are professors. And go to Google image search and say bozos, basically, are non-professors. Okay? And then non-professors will come. Then you train neural network that as the non-professors. You would clearly should not be surprised when in fact, this trained network is likely to say that most non-male pictures have low probability of being professors. Do you understand why? Because if you actually do, some of you, the two of you guys, the man next to you, excuse me. If you want to use the laptop, come sit in the front. So I know that you're actually paying attention to the class. Okay? Or if you're using the laptop, use it for something useful, such as search Google. The same for the other guys using the laptops. The nice round is over. So now midterm is over. So you want to stay in the class, you pay attention to me, or don't show up to the class. That's fine. And then you just do your attendance. That's fine. So it turns out that on video, I don't have this problem. So if you're watching my video, while watching it, if you're taking shower or doing something else, it doesn't matter to me. But in front of me, pay attention. Okay, so if you do this, if you search Google for images of professors, just right now in front of me, and you see image search, you would see in the top 100, probably 18% are men, maybe 90% are men. So what is the bias here? And this is much harder. So in fact, if the government was to regulate biases in learned systems, it's so much easier if all they have to do is look at the code and say, my God, these guys sneaked in something about gender and race and hair length. That you can check. But it's much harder if what you have to do is tell me the data on which you trained yourself. And then let's look at this data. So that's why it's an interesting problem. Algorithmic bias is a simplistic problem. Nobody has to worry about it because, at least as I said, we have reformed by hypocrisy. Nobody is going to write, if the guy is brown, put them in jail. Those days are over. Okay. Now the bias would come in very indirect and somewhat insidious ways. And that sort of brings it here. That's, certain aspects of that same bias is why we can see dogs and birds everywhere. Okay? Yes, sir.
If a majority of professors, I don't know if this is true, but if a majority of professors are male, wouldn't you want your neural net, your data to have that bias?
That's actually a very beautiful question, and these are things that I'm happy to talk. I will answer your question, but these are sorts of things that we should think about. There is my answer to that is, what are you using the learned system for? Okay, the learned system is basically representing the current data. It's representing the current snapshot of the society. Okay, if you are holding, okay, like a party for the professors this evening, okay, based on your statistics, you can decide more males than females will show up. That's statistically true. So perhaps you will build more male restrooms and fewer female restrooms. But one of the things that we wind up doing is we use the same learned system to plan for the future. You know, if you build real restrooms, they will be staying here for 20, 30 years. And you know, I have seen, I mean, it's in fact, there is a person, Mary Anderson Rowland, who is still a professor in our department, you know, CDC department. She has worked in ASU for 40 years. And she was telling, last year in CS night, we gave her like a celebratory thing. And then she was telling us about her memories from the time when she joined ASU. There was actually no female restrooms around in engineering colleges. Because females don't need it, and they weren't it. Okay? And so again, some of these things essentially, it's not that anybody is sitting down and making insidious decisions. You know, you can do a lot more damage by using patterns that you found that are about current society in planning for the future society. And that's a huge issue, because if we believe that we have reached a level of perfection that the current society should be the same as future society, then you can just use the exact numbers and statistics that you have about it. But unfortunately, we believe that we are never perfect. And so you should be very careful. So that's one way of thinking about it. There are many other things, but that's one way of thinking about it. Okay, so we also talked about the fact that the gradient descent can be done in like these three different ways: batch versus mini batch versus stochastic gradient descent. Batch, of course, is you compute the error on the entire data set and then do the gradient for that entire error, and then you change the weights using the entire error. Okay. Now, that obviously you may have noisy samples, and because of the noisy samples, there may be some particular examples are actually noisy, and so there may be error on them, even though network is actually should have been considered to be right. You know, because noisy samples can come when it's a dog picture, but I wrongly labeled it as a cat. And so the network actually is saying it's a dog, but because of my labeling, it will be told, no, you should have seen it to be a cat. And so on that particular example, it's being wrongly shifted towards the wrong answer rather than towards the right answer. Right? If you take the error over a large number of samples, then these local inconsistencies will sort of disappear to some extent, and so the gradient would be in the right direction over the entire ensemble. So in fact, batch is considered to be a better way in terms of the robustness